Folks, picking up right where we left off. So I'm starting off on this slide right here, again, to remind you of this Heisenberg uncertainty principle and Schrodinger's wave equations. So again, this idea that because electrons are both particles and waves, it's very difficult to know their position or their momentum simultaneously with any arbitrary level of precision. So instead of orbits, we use orbitals, and that's what we're going to be talking about in this next video. And an orbital it's a mathematical solution to the Schrodinger's wave equations, okay? But this mathematical solution, it's a three-dimensional mathematical solution. So these orbitals are shapes, and what they represent are probability distributions or regions where you will likely find the electron. And again, we start by noting that the higher the value of psi squared, this probability value, the more likely it is to find it. The lower the value of this psi squared probability, the lower the likelihood that you will find the electron. And where we're talking about finding it, we literally mean in this radial position as indicated in this graph right here, okay? So let's see. So the first one we're going to talk about are s orbitals, okay? So we noted for an s orbital, you have to have L equal to 0. And we can have s orbitals for n equals 1 all the way down to n is equal to 6. We can go all the way up to 6s as long as L is equal to 0. Okay? And so these s orbitals end up having a spherical geometry. So for now, let's just pick on this 1s orbital. Okay? So we have these two equations here that we're going to talk about. So total nodes are n minus 1. So that means 1s has 0 nodes because 1 minus 1 is 0. So an s orbital is literally just a sphere, okay? And within that sphere, within that three-dimensional sphere, that represents the probability of finding the electron, okay? So for example, if my nucleus is right here in the center of that 1s orbital, then it is likely to find the electron anywhere in this orange region, okay? So I have a really cool computer simulation I want to show you. So this is for my CHEM 362 class. And they solved the Schrodinger equations using this Mathematica program. So I'm going to also be sharing with you some of these results here. And so you can see all the equations and stuff. You don't have to know all this stuff. You don't have to know this code. It gets pretty nasty. But here is our 1s orbital. So it just becomes a sphere. Okay. So for example, if we had a 1s electron, it could be anywhere within this sphere. Anywhere within this three-dimensional object represents the likely places of finding that electron. Okay. So now what about all of this node business and the 2s and the 3s and all that stuff? What does all of that mean? Okay. Well, total nodes are n minus 1. So when we go to 2s, you can see that we have one. Let me write this a little bit better. Okay, so I'm just going to say here this number that I'm referring to is the total number of nodes. Okay, and so we recognize that 2s has one total node. Okay, so what kind of node is it? Well, in terms of nodes, we have radial or angular. Okay, and they both have to add up. So I'll actually say, I'll erase that once again. So I'll say radial nodes and angular nodes, and radial plus angular equals the total. So you can see I've got an equation for the radial nodes right there, n minus 1 minus L. Okay, So here this is total right here. And then now we can calculate the radial nodes. And so obviously for the 1s, it's going to be 0. But what about 2s? Well, if it's 2s, L is equal to 0 and N is equal to 2, right? So that becomes 2 minus 1 minus 0, which means 2s has, I ran out of room here, 2s has 0 angular nodes, but 1 radial node. What is that radial node? Here it is, okay? So technically, that's a radial node, and it's radial because you can see it's based on some mean radius, right? I can draw an arrow, and that represents the radius of that node, okay? So what about 3s? Well, we recognize that 3s has got to be 2 minus 1 to give me 2 nodes in total, okay? So it's going to be 3 minus 1 minus L, which is also 2. So all of those nodes in 3s are radial nodes, and you can see here they are, 1, 2, okay? Well, what if we were to do 4s? Well, as you might imagine, 4s should have 3 total nodes, and all 3 of those are radial. So that means 4s, we would have, 1 node, 2 nodes, 3 nodes, and even a 4th node. And so I know my picture doesn't look very nice. But now what these nodes mean, okay? So this picture that you're really seeing here is a cross section, all right? So from the outside, a 3s orbital will still have that spherical shape, okay, from the outside. But if we were to slice it, if we were to slice this in half, right, that gives us the cross section. And what we would see is like these little onion layers. And the white regions, okay, those are the nodes. So that's where there's 0 probability of finding the electron. So a node equals 0 probability, okay? And so what this orange represents, so I'll draw an arrow to the orange region, that represents probability. And I'll even go on to call that finite probability, okay? So another way we could view those pictures are like the following. So if I look at now all of these little dots, okay, those little dots are kind of like the shaded areas you were seeing before. So let's say dots represent possible electron positions, okay? So if we did these calculations hundreds or millions of times, all of these little spots represent probable electron positions. And what is observable, what you will notice are those kinds of onion layers. So for example, if we first start at the 1s, we can see there's no internal radial nodes, okay? So in other words, if I made a 2-dimensional graph out of this shape, it would just be one really large peak, and you can see that peak corresponds to where the electron density is the highest. So that gives us the most likely place to find the electron. And you can see if I trace where that peak is, it's something like maybe, I don't know, 100 picometers away from the radius, or away from the center, right? So if I looked at the center, that most likely place is like somewhere right here, right? So it does kind of look like an orbit, but because it makes this 3-dimensional shape, we call it an orbital, all right? So that's due to n is equal to 1, L is equal to 0. So now if I go to 2s, n is equal to 2, L is equal to 0, that gives me, remember, 2 minus 1 minus 0 equals 1 for 2s, okay? So now there's that one single node. There it is, okay? And it just so happens to be a radial node because of this spherical radial geometry, all right? And so here you can see that node right there. It's kind of tough to see it on the picture, but right, you can see where that gap is, where there's no electron positions. That's what makes up the node, all right? And so now when we go to 3s, right, 3 and 0, 3 minus 1 minus 0 equals 2. And so there's my 2 radial nodes, okay? And you can see they're given by these areas, these regions of no electron density, all right? And what you also notice, based on the height of the peak for 3s, that's the most likely position. For 2s, that's most likely. And you can see for 1s, there's only one peak, so that's the most likely place. So the other trend that you should observe from this is as we go from 1s to 2s to 3s, they get bigger, okay? So going from 1s all the way to 6s, the size of these orbitals are getting bigger. So we're predicting that the atoms are getting bigger because those electron densities are getting further and further away from the nucleus, okay? All that being said, look, there is still some, I'll say still some probability of finding those electrons in the inner layers. It's not 0, but it's still smaller than the most likely position, okay? So it's still somewhat finite, but the most likely positions as the orbitals get bigger are to go further and further away from the nucleus, okay? So let's move on to the p orbitals, okay? So when we have n is equal to 2, we can have 2s, which we just described. We talked about 1s, 2s, and 3s. But when L is equal to 1, we can have 2p, okay? And I made note that because there's 3 ml numbers, that gives us 3 orbitals, so thus we get 3 p orbitals, and here they are, 2px, 2py, and 2pz. We could also have 3px, 3py, 3pz. We could have 5px, 5py, 5pz. We could have all of those, okay? We could definitely get into those. And we can definitely have nodes, radial nodes for these. But what we're also going to see, in addition to having radial nodes with the p orbital, there's also angular nodes. So I'm going to try to draw here the difference between those two, okay? So now if here's my p orbital, all right? So as it turns out, let me do a different color, okay? So this area right here and this area right here that's empty, so I'll say like this and this angle theta and this angle theta, those represent an angular node. And we're going to calculate how many there should be, okay, in a moment. So how do we represent radial nodes? Well, the radial nodes are going to be internal. Just like we saw with the s orbitals, those radial nodes make those internal nodes, okay? Well, as it turns out, p orbitals can also have these types of onion shells, okay? So 2p, so we have to kind of inspect here, are they going to have any, and what is that going to be, right? So for 2p, we recognize the total nodes will be 1, because it's always n minus 1 for the total, and n minus 1 minus L for the radial, all right? So for 2p, that's 1 total node. But what about the radial nodes? Well, n is equal to 2 and L is equal to 1. So 2 minus 1 is 0. So 2p has 0 radial nodes, okay? So that means 2p's only node is angular. It just has one angular node. And I know when you're looking on here, it looks like there's two. But this is represented, so they're the same angular node. What it really does is it makes like a stair radian. It makes like a solid angle, okay? So 2p only has one angular node. Well, what about 3p? Okay, well, we know 3p has two in total, right? Okay, it has two total nodes. So how many radial nodes will 3p have? Well, it's going to have 3 minus 1 minus 1, which is 1. So that means 3p has one angular node and one radial node, and this is it. So this is a 3p orbital that I'm showing you right here. And so these, these solid angles, these discluded areas that I've indicated, those are your angular nodes. The radial node is internal. And we'll see that on a graph here in a moment. But what I want to switch to is my Mathematica simulation here that I have my 362 students do. And so here we go. Here's the 2p orbitals. Here's all of the equations. And so this is the calculation of the 2pz orbital. Okay. This is the calculation of the 2px. Oop, it got small when I flipped it around. Here's the calculation of the 2py, and here is now putting them all together. Okay? So when we put 2px, 2py, 2pz together, it does make this pretty cool shape. It is this three-dimensional shape. And we're going to see in chapter 8 how this shape will manifest into the shapes of a molecule. So for now, this is just what a random electron would look like in a single atom. But this will get connected. We will connect this to how this determines the shape of molecules, which is pretty cool. Okay, so here you can see that on this slide as well, right? The 2px, 2py, 2pz, and then the total view of all of them together. Okay. So if we look at the radial profiles of the p orbitals, okay, then here's where we're going to start to see some interesting stuff. Okay, so we noted that nodal plane is part of that angular node that I was talking about. It's part of that discluded area, okay, from the two lobes. And so if we were to look at the graph now, if we look at 2p, for example, we notice here 2p, the red curve, it does not have any radial nodes. So 2p equals 0 radial nodes. And we see that on this graph, right? It's just one peak, all right? What's also interesting, what we're going to start to see as well, is when we start putting these probabilities together with 1s, 2s, and 2p, they all start overlapping with each other. And that's going to create electron interference. So a 2s orbital will definitely interfere with a 2p orbital because they're similar in size. So they have their most probable positions in a very similar location. Okay. But we also notice that the nodes, so now the green curve is 2s. We also notice now, because of those nodes, we can distinguish on these types of graphs what orbitals they are based off of these two equations. Okay? So like, for example, I note that 2p should be very close to 2s because they're both level 2, so they both should be very close. However, 2p will not have any radial nodes. However, 3s will. Okay? So we're going to see more of this stuff when we put together the remaining orbitals. All right? So 3D gets a little bit more complicated. And we noted because there's 5 ML numbers, there should be 5 3D shapes. You don't have to memorize the names of these as long as you recognize there's 5. And they get rather complicated. So in the positive and negative signs are based on the quadrant that they're in. So again, that's not super important for this discussion, but we can see that those positive signs give us, they alternate, which is kind of to be expected. So those are based, again, on the quadrants that they're located in, okay? So there's the dxz, the dyz, the dxy, the dx squared minus y squared, and the dz squared is the one oddball here, okay? And so with 3D, we can calculate the total nodes. N minus 1 equals, so we should see two total nodes for 3D. How many of them are radial? Well, that's N minus 1 minus L. So for 3D, that's going to be 3 minus 1 minus 2 equals, just like the 2p, there's 0 radial nodes with 3D. However, 4D will have some radial nodes, and those radial nodes are internal to the structure. So on my Mathematica calculation here, so the equations get more complicated, the more complicated the orbitals get. And so here is that 3dz squared, and this is pretty cool. I can kind of move it around in this Mathematica calculation. And so here are the other 4 3D orbitals. And I can put them all together, and when you put them all together, it's pretty cool, right? They actually all, each of those lobes, as crazy as it looks, each of those lobes, you know, fit together really nicely, okay? This is also why when atoms get really complicated, when atoms have a lot of electrons, we just approximate them as a sphere, right? Because we notice here there's lobes where each of these electrons could be located. And, you know, for something like iron or titanium or, you know, something that has like 50 plus electrons, it just begins to start to look like a sphere. There's electron, you know, lobes, there's electron density located kind of all over, which gets pretty cool, okay? So now if I move forward here so we can see some of that when we start to talk about these d orbitals. So I noted that there's 2 nodes for 3D, and those are going to be angular. And you can see those indicated right here, right, by these nodal planes. Okay, so now in the P there was only 1 nodal plane, but in the D there now becomes 2 nodal planes. And now if we look at the probabilities here, we note that 3D, remember 3D has 0 radial nodes, okay? 4S should have 1, 2, 3 radial nodes for 4S. 4P will only have 2, 1, 2. So as you can tell by now, I've been going through these equations for like several lectures now. So you should be really comfortable with doing the math and coming up with these various nodes and what these distributions would look like on our chi-squared versus radius graph, okay? And so the last one I'll describe is the F, and I'm not going to spend a lot of time with this because these get wholly ungodly complicated, and I didn't do these in the Mathematica simulation. But you can see 7 of these things, and here they are, 1, 2, 3, 4, 5, 6, 7, and they get complicated. They get really complicated, okay? And what I want to point out now, so as you might start to guess, when we start to pile up all of these orbitals on top of each other, and in other words, when we get to the complicated atoms, the atoms that have 4F or 3D electrons, okay? They start interfering with each other, and we call that interference penetration. So I'll write interference, okay? So in other words, the electrons are getting really close to each other, right? You can see the 3D, the 3P, and the 3S. They're all like predicted to have similar distances from the nucleus. So that means because they interfere with each other, they cause the levels to split, all right? And the order goes S, P, D, F. just like we learned from the quantum number rules. Okay? And in a moment, I'm going to show you a fantastic way to remember this order. You don't have to memorize it as long as you can remember it. And where we're going next, I'm going to give a little foreshadowing to where we're going next, which will be a next video. But now when we get into these orbital energy level diagrams, because all these orbitals get complicated, we have to have a more simplified way of representing them. And we do that with these diagrams. So these diagrams are our simplified way of representing these complicated polyelectronic atoms. So atoms containing more than one electron. So we started with this, with our basic energy level diagram, 1, 2, 3, and 4. Okay? And for hydrogen and hydrogen only, when we put the orbital designations on, this is what happens. Look, n is equal to 1 becomes 1s. But look, n is equal to 2, it has 2s and 2p. And for hydrogen and hydrogen only, 2s and 2p are degenerate, which means it's a fancy way of saying the same. It means they have the same energy. Okay? And we notice what happens to n is equal to 3 for hydrogen and hydrogen only. 3s, 3p, and 3d are all predicted to be at the same level. Same with 4, 4s, 4p, 4d, 4f. They're all predicted to be the same. However, as soon as we put multiple electrons in there, those levels interfere with each other and they cause them to split. Because, for one, electrons repel other electrons. That's the particle interaction. But electrons also interfere with other electrons. That's the wave interaction. And this order becomes S is less than P, which is less than D, which is less than F. So now what happens in these levels, we start at 1s, and then going up in energy gives us the correct order. So we start at 1s, and remember, we still call this the ground state, or the ground level, okay? 1s, 2s, and then now look, 2s and 2p are no longer equal. 2p is slightly higher than 2s, okay? So it splits. And then now, we know that level 3 has to be higher than level 2, okay? So 3s is higher than 2p. But now look, 3p becomes higher than 3s. And this is where it becomes a mess. Because now, as it turns out, you would expect that 3d would be next. But as it turns out, 4s is slightly lower in energy than 3d. So then it goes 1s, 2s, 2p, 3s, 3p, 4s, then 3d, then 4p, then 5s, then 4d. It becomes a mess. And in fact, here is the full periodic table right here. So this is the full table. And as you might guess, like look, so this is showing you in order, right? 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d. So how do we keep track of that order? Well, I'm going to back up for a second and go back to our periodic table. Okay, this. Quantum numbers are the address of an electron on the periodic table. So the way we remember that order is by starting here with hydrogen. We start here and we move from left to right, top to bottom. Okay? Left to right, top to bottom. And then check it out. So this order goes 1s to start, okay? And then next is 2s. And then look, next is 2p. And then next is 3s. And then we keep scanning across. And then 3p. And then 4s. And then now look, it goes 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. We can literally go left to right, top to bottom, and that is the correct order for these energy level diagrams right here, okay? So this complicated mess of order, it's just unraveling the periodic table. So instead of looking at the periodic table from left to right, top to bottom, this just starts with an energy level diagram of every single position on the periodic table. And that's what we're going to see in the next lecture. Each one of these spaces represents a position on the table. Okay? And we're going to go through this. We're going to do this outbound principle. Electrons are added one at a time to each successive orbital in order of energy. We're going to go through it and do it on the next video. Okay, folks? Hasta luego.